notice that this is quite fast here, so it gives us a large time step. And first of all, we have nice circular, little bit elliptical orbits, and then one of them got flung out. There was the pink one, and two of them collided. Now those collided, and now we get nice ellipses of the remaining two. I'm going to repeat that, this time without the traces, even though the traces do look beautiful. And yeah, the underlying principle for anything that happens here is the gravitational law that is being applied over and over again between these four bodies. And the problem is very difficult computationally. And there's the collision. And why did it make zigzag? Well, that's because it had a gravitational attraction to something else, and now it goes on. And I did say, actually, that I would turn the traces off, so I will do that the third time. There we go. Yep, just gravitation behind these. All right, and then the same thing will happen, and there's the collision. And the yellow one is attracted to the pink and the blue one, and that's only why it's the reason why it looked so strange, but that's all that there is behind is the gravitational law. And these two remaining ones on their ellipses orbiting each other. All right. Reset. And now the next one is, I'm going to put the exact same scenario, but I'm going to make it more accurate. So I'm going to go half the speed, I guess this one is here. And it's the same starting conditions, but now it's calculating more accurately with that time step, not being as fast. So far, it looks just the same as the other one. And let's see, okay, now things might start to happen. There we go. All right, there's a collision, but it wasn't the same as the other two earlier. And notice the pink one doesn't come back. And the other two, they're actually off the screen. I saw them going off on the left. Reset. This time do it with traces. So with a different time step in these computations, we get a totally different outcome. So we can only predict so much when doing these kinds of computations with just one basic gravitational law between these four here, of course, applied several times because there are four interacting bodies. And the outcome is different depending on the time step that we use. So this is going to be the most accurate one. And this will take a while, obviously. And again, the outcome will be different. So on the three-body problem, that's just a collective term for anything that acts under the gravitational law with more than two bodies. It is very sensitive to the time step that is being used in the computations, even though the starting conditions are exactly the same. So when we look at our own solar system, then we have to see that if we give it more time and want to compute it, what will happen to it in the future? Well, we just can't because we don't have the computation power. By the way, off screen, the yellow one just collided with the green one. These two here are orbiting each other, going slightly off the screen. The yellow one, by the way, is coming back because it is attracted to the other two that just went off the screen. They're all coming. The three remaining ones are going to come back here in a moment. So there they are, and we will see that here, now that the yellow one is getting closer, it influences the other two, and it actually ejects the pink one and keeps the blue one, so the blue and the yellow one are orbiting each other. again, different outcome as before. I guess the half-fast one also was kind of like that, but notice they actually went off to the upper left, not to the lower left. All right.